So welcome to our next lecture involving Gibbs free energy, and we'll see what else we can do with it. So let's consider a nice, simple, straightforward reaction. Silver nitrate in aqueous solution plus sodium chloride in aqueous solution are mixed together, and you produce silver chloride and sodium nitrate. What's the delta H0 for this reaction? What's the delta S0 for this reaction? And so what's the consequence delta G0 for this reaction? Pause the video, take a few minutes to do the calculation, look up the stuff and do the calculation. Yes, some of those compounds are not listed in the table in the back of the book as far as thermodynamic properties are concerned. But all the ionic compounds are clearly going to simply be their ions in solution, and so you can look up the ions that make up the necessary combination to do the calculation. Go through and find out it's an exothermic reaction. Bond formation, we're bringing stuff together, is exothermic to the tune of minus 65,000 kilojoules. And of course the entropy is dropping. We're going from a solution full of ions down to a solid. That's automatically going to include a drop in entropy. And the entropy drop minus 34 joules per Kelvin. So delta G is the minus 65,000 joules. Minus 298 times the minus 34 joules gives us an answer of minus 54.9 kilojoules. If you go through that calculation, you'll notice that the energy and entropy for the sodium is added in and then subtracted out. And the same is true for the nitrates. Their values are added in and then subtracted out. Because, of course, they're spectator ions. We only actually needed the net ionic equation, the data for the silver ions and the chloride ions forming silver chloride. Those were the only ones that were actually reacting. So let's consider the reverse reaction for a minute. Solid silver chloride forming silver ions and chloride ions in solution. What would the delta G0 be for this? Well, fairly obviously, it would simply have the same value but the opposite sign as the delta G for the above reaction. So it'd be plus 54.9 kilojoules. A very unfavorable delta G0, so that means it would never happen. Well, never happen? You do have to keep in mind, delta G0 is a very specific set of conditions. 1 atmosphere, 25 Celsius, 1 molar in solution. Delta G is the actual requirement that has to be negative for the reaction to run, not delta G0. And what's the difference between delta G and delta G0? Well, the point is delta G0 is a very specific set of conditions. Delta G refers to any set of conditions. And so there has to be some relationship between delta G0 and delta G, and what is it going to involve? Well, obviously, the first thing you could change, which would change everything's energy, is temperature. And so our modification to delta G0 is going to have to include a temperature term. What else would we change? Well, obviously, we can change either the pressure or the concentrations of things. And so we have an expression Q. And Q is simply equal to the concentration of the products or their pressures divided by the reactants. And last but not least, of course, Q is a log term, so it's neutral. T is in temperature. Delta G is in joules. So we're going to need a conversion factor that changes something in temperature into joules. And once again, we see our friend R, the universal gas constant, in its form as an energy conversion term, 8.314 joules per mole Kelvin. So delta G the Gibbs free under any conditions, is related to delta G0, which is under specific conditions, plus RT log Q, where Q is concentration of products over the concentration of reactants. One of the things you might notice from this equation is that when the concentration of products is 0, delta G goes to minus infinity, which means basically something, when you mix stuff together, something's going to happen, because having something happen is extremely favorable. When delta G is positive, nothing's going to happen. Actually, the reaction prefers to run in the opposite direction. When delta G is negative, stuff can be happening. Things are changing. The obvious break point between those two is when G equals 0. Delta G equals 0, which means the stuff stops happening. Well, what do you call it when you're talking about a reaction to when the stuff stops happening? That, of course, is equilibrium. The condition of delta G equals 0 is the equilibrium requirement. So now we can go back to our friend, the silver chloride. So at equilibrium, delta G would be 0. That would be equal to RT log K plus delta G 0. Well, the delta G 0, we said, for that reaction was 54.9 kilojoules, plus the 8.314 joules per mole Kelvin times 298 Kelvin times the log of the KSP. So the log of the KSP is equal to minus 54,900 joules divided by 8.314 divided by 298, and that's minus 22.16. So KSP is e to the minus 22.16, or 2.4 times 10 to the 10th. And so we have a way of getting solubility constants. All we have to do is calculate delta G0 and set that equal to RT log K, and we get an answer. Let's consider another simple reaction. For example, changing methanol liquid into methanol gas at room temperature. We'll have to look up the delta H's and the delta S's so that we can get the delta G of this process. And we find out, not surprisingly, it's an endothermic process, plus 380 kilojoules per mole, which is what you'd expect. Changing the liquid to the gas is going to be an endothermic process. In the same way, of course, it has a positive entropy change. The gas is going to have a lot more entropy than the liquid does, plus 113 joules per Kelvin. Do our calculations for delta G0 at 25 degrees, and we find plus 34.7 kilojoules. So this reaction is not favorable at room temperature, which is what you'd expect. Methanol is a liquid at room temperature. Well, at what temperature would this reaction become favorable? Well, it would become favorable when the entropy term overtakes the heat reaction term. And what temperature is that going to be? Well, at the point where they overtake, delta G would be 0. And so we can calculate T. It's going to be delta H divided by delta S. And we go through, find out it's 336 Kelvin, that is 63 degrees Celsius, which is actually very close to the real value, which is 65 degrees Celsius. And so we can use delta G and delta H and delta S to get things like boiling points, where the transitions will in fact take place. And that concludes our lecture today on Gibbs free energy terms. And so I'll see you next time.